Do any of you guys travel from off campus to get to school? You guys all live on campus? Okay. The weather this week is supposed to get really bad, Tuesday and then going into Wednesday. If the National Weather Service is at all accurate, we'll get about 12 inches of snow on Tuesday and Wednesday. Sorry. Sorry, that's the way it is. Since you guys are all on campus, I live 9 blocks away. I can always walk in if I need to, so let's just plan on being here on Wednesday. If something changes, I'll send something out probably late in the evening, Tuesday evening, probably before 10, but not probably before 5 because I'll just be monitoring weather. But plan for now to just be here, and we'll do what we normally do here in person. If we don't meet in person, we can meet on Zoom, and I'll send you out a Zoom request at that point. Any questions over what we were going through last Friday or last week in general? All right, who can tell me what the central limit theorem says? Yeah. Normal distribution of the sample? Of the sample means, yeah. You wanted to add something?
Something, don't you have to do it like 1,000 times or something?
Yeah, so that's what you create a distribution of sample means. So if you have a population, and it doesn't matter what the shape of that population, if you go into this population, you take a sample. Let's say that that sample is as small as just 2 observations. Take those 2 observations, get the mean of sample 1, throw those 2 observations back into the population, grab 2 more samples, 2 more observations at random, calculate the mean of that, throw those 2 observations back in, get 2 more, take a mean of that, throw those back in, grab 2 more, take the mean of that, all the way up to, let's just say 10,000 samples. This will create a distribution of sample means, and that distribution will be centered at the population mean, and it will be normally distributed. Okay? So it got to be too much, didn't it? Sorry. I really don't like the way they've reconfigured the room very much. It inhibits me at the board. So that's what the central limit theorem says. And the cool thing about that is that every parametric test that you run relies on the fact that the distribution of sample means is normal. And the nice thing about that is that virtually every distribution of sample means is going to be normal, regardless of the shape of the original population. This is the shape of the original population. What does the empirical rule tell us? Somebody other than Elizabeth. Yeah. Okay, so it describes the area under the curve for a normal distribution at different levels of deviation from the mean of that distribution. So if you go out 1 standard deviation from the mean, it's about 68% of the population. Almost 2 standard deviations from the mean includes 95% of the population. 3 standard deviations includes 99%. So it's this regularity of the normal curve that allows us to say how many of the observations are found 1 standard deviation away, 1.96 standard deviations away, etc. This, once again, is how we then determine our confidence intervals, how many standard deviations we're going away from the mean in order to make sure that we're encompassing a certain proportion of the observations within that distribution. These two things in combination are the secret to virtually every statistical test on the planet, if it's a parametric test. There are non-parametric tests that don't rely on this, but parametric tests, t-tests, ANOVAs, linear regressions, all of these kinds of tests rely on these two things working. So the question is, does this actually work? So there's an R script on last week's materials that basically deals with the Spanish flu data set, the flu pandemic of 1918, this pandemic that swept around the globe, killed between 25 and 50 million people globally. It's responsible for all sorts of changes that occurred in the 1920s, but this is a data set that records essentially the date of death of the population of people in Switzerland during the pandemic. And what you can see is that this is a very non-normal population of death. So very young individuals died a lot, but of course back in 1918, very young individuals died a lot anyway. So this may or may not be due to the flu, but then young adults died and old people died a lot more than people did in their Middle Ages. And so this is what we would refer to as a non-normal distribution of data. It's a tri-modal distribution of data. A mode at the very bottom of the age distribution, a mode kind of in the early adult years, and a mode in later years. Well, what we can do is we can go to this population of individuals and we can select 2 individuals out of this population, calculate their average age, store that, throw those 2 individuals back in the population, nab 2 more individuals at random from the population, calculate the average age that they died at, record that, store that, throw them back in the population, grab 2 more individuals, look at their age of death, and do this over and over and over again until you build up a distribution of sample means. You're basically taking the average age of death for 2 individuals 10,000 times. And what you get when you do that is this distribution. This is the script. This is what the script will produce when you run it on your own. And what you see is that it's not normal yet. The red line is the theoretical normal based on the spread of the data. The observed density curve is in blue, but this is certainly way more normal of a curve than this was. These are the original data. This is the curve that you get when you sample it, calculate the sample means. So this is a distribution of sample means as opposed to this is the raw data. And this is for only 2 observations, which is a really small sample size. But you're already way closer to a normal curve than you would be if you were just looking at the original data. We can increase that to looking at 4 individuals. Grab 4 individuals, take the average date of death or average age of death, save that, throw those individuals back in the pool, grab 4 more, average, store, throw them back, grab 4 more, average, store, throw them back. Over and over again, do that 10,000 times. And now you see that the population is beginning to look pretty normal. The blue line, which is the observed density distribution, is looking very close to the red line. What do you think is going to happen if we increase the sample size? It's going to get closer to normal. What else is going to happen to it? Go back here. What else do you notice changing about these distributions? It's getting taller and narrower, isn't it? So at 2, it ranges from 0 up to probably late 80s for the average. Get to 4, still down here at 0, but this has crept back down to the early 80s, late 70s probably. Take 10 individuals, get the average, store it, throw them back in. Take 10 more individuals, get the average, store it, throw them back in. Over and over and over again. The theoretical normal and the observed distribution are now very close to one another, and you've lost the tails of this thing altogether. This thing is getting narrower and narrower. As it gets narrow, it also gets more pronouncedly peaked. Get up to 30 individuals, and once again, this is very close to a normal distribution. It would probably be statistically indistinguishable from a normal distribution. And once again, this has narrowed in. What are you honing in on as this distribution gets narrower and narrower and narrower? What parameter are you honing in on? From over here. You're honing in on the population mean. The sample mean is an estimate of the population mean. If you only have 2 individuals that you sample from a population, do you have a very good idea of where the population mean is? Is that estimate of the population mean going to be very good? Probably not. If you have 4 individuals, is it going to be better? Yeah. If you have 10 individuals, is it going to be even better? If you have 30 individuals, is it going to be even better? Is it going to estimate the population mean exactly? No, probably not, because of sampling error. This is one of the errors that we can talk about. But sampling error is just the deviation of the sample mean from the population mean due to the fact that we're just sampling. For any given sample of 2 individuals, we could randomly select an individual down here and an individual down here. In the next sample, we could actually end up selecting an individual down here and an individual here. In the case of selecting one here and one here, you would get a sample mean that is pretty close to the population mean. But if you collected an individual here and an individual here, you would get an estimate that was considerably smaller than the sample mean. So for a sample size of 2, you lack confidence that the sample mean is equal to or even close to the population mean. And we shorthand the population mean with the Greek letter mu. So we're shooting for the population mean, but we're not particularly accurate because we only have 2 data points to try and hone in on what that population mean is. So we have some idea of where the population mean is, but we don't have a very good idea of where the population mean is. we use a sample of 4, we have a better idea of where the population mean is. Sample of 10, an even better idea of where the population mean is. A sample of 30, and we have an even better idea of where the population mean is. I had a stats professor in grad school. His name was Patrick Phillips. He said, 30 is a lot closer to infinity than it is to 0. And what he meant by that is that if you were to draw a graph that basically showed you, the confidence you have in the sample mean and sample size, as you gather larger and larger samples, your confidence in the sample mean, in terms of it predicting what the population mean, goes up pretty swiftly. And it starts to level out at around 30. And adding more sample doesn't really improve your estimation of the population mean beyond that. So you could spend a lot more money gathering more samples than 30, but it's not really going to gain you much in terms of statistical power, because your big gains in statistical power occur as you go from 1 sample to 2 samples to 3 samples to 4 samples to 5 samples. Adding 5 samples here makes a huge difference in your ability to get a good estimate of the population mean. Adding 5 samples out here gains you almost nothing in terms of improvement in your ability to estimate the population mean. So 30 is a good walking around number. If you ever want to ask yourself, well, how big does my sample need to be, and you don't want to do any preliminary research or anything else, the first answer is always 30. Now, does that mean you can get away with fewer samples than that? Sure. But once you get to 30, you're kind of in that sweet spot where adding more samples to your sampling scheme doesn't actually gain you anything appreciably. So that's never actually dubbed it formally this, but that's the Phillips Rule, after Patrick Phillips, who taught me stats in my doctoral dissertation institution. Any questions about this fundamental concept? So far we've talked about the need for samples, and the samples have to be representative, random, and independent of one another. They need to maximize precision, repeatability, and accuracy, and minimize bias. The empirical rule combined with the central limit theorem are the basis for all of our parametric tests that we're going to talk about. And increasing sample size in experiments can compensate for non-normal data, but there is a point where you reach diminishing returns, where adding more samples don't really gain you much in terms of statistical power. So that's kind of what we've gone through so far. That all seemed to make sense, resonate with you. Okay. Because as our sample size goes up, our confidence in our ability to estimate the population mean also goes up. We have to account for that when we're calculating statistics. So So we'll talk about how you go about calculating confidence intervals after we talk about the different types of data. The concepts that we've been talking about so far, the central limit theorem, the empirical rule, they only apply to quantitative data. So we have data that are of different types. So we have qualitative data and we have quantitative data. And you can do different things with these different types of data. One type of data is not better than another type of data. They're just different. So you can have two different kinds of qualitative data. We have nominal data and we have ordinal data. Do you guys know the difference between nominal and ordinal data?
Ordinal has an order to it.
Okay, so ordinal has an order to it. Nominal data is just names. I have on the board on the screen things like gender, race, religion. Males are not any better than females. Females are not any better than males. They're just different, male, female. Religion. Protestant is not any better than agnostic, which is not any better than Catholic, which is not any better than Muslim, which is not any better than Jewish. They're all just categories. They're names that you can put to a person based on what their faith tradition is. So nominal data are just things that you can name. Yellow, orange, green, blue. Now, I'm of the opinion that blue is the best color, but that's my opinion. There's no rational argument that I can make for why blue is superior to yellow. This is what nominal data are. And you can analyze nominal data and ordinal data using things like chi-square tests that are tests of distribution. So we could survey the color of shirts that people are wearing today, and we have green. What would you call that shirt? Go with your undershirt is purple. Purple. We have blue. We have two black, two gray, peach. What is that? Pink? Oh, okay, pink. I'm a dude, I can't do color. Oh, there's three black now. So we can actually count up the different colors that people are wearing. I'm wearing green, so that's one individual, 2, 3. I'm wearing green. There's one person wearing pink, one person with purple, 2 with blue, 3 with black, and 2 with gray. And we could ask questions about that. We could ask the question, are all colors of shirts represented equally? Oh, there are 4 with black. 4 with black. We could ask, are all shirt colors represented equally? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 individuals. We have 1, 2, 3, 4, 5, 6 categories. 11 divided by 6. So about 1.7. So the expectation is that a uniform distribution would look like this. This is what we would expect if everybody came to class wearing different colors of shirts in an expected uniform distribution. And then we could use a chi-square test to ask, does the distribution that we observe differ from the distribution that we would expect? That's the kind of statistical test you can do with nominal data. You can do a chi-square test with ordinal data also. Ordinal data are just data that once again can be ranked. Do you agree with this statement? Paul Rock's applied statistics. We can strongly agree. You can strongly disagree. You can disagree. You're neutral about the issue. You agree or you strongly agree. These are, once again, categories. They're names that have been stuck on things, but they can be ranked from presumably worst to best. So they have an order to them. This is what ordinal data, this is the nature of ordinal data. So sizes, small, medium, large, attitudes on things like Likert scale, surveys and things like this. There are 11 of you. Are there 11 of you in here? 1, 2, 3, 4, 5, 8, 9, 10, 11. I counted correctly earlier. So there are 11 of you here. Maybe 3 of you think that I'm not rocking it today. 2 of you disagree. 4 of you are neutral. 7, 8, 9. 1 of you agrees, and 1 of you strongly agrees. So we could create a distribution of that and then ask ourselves, does it match or differ from some expected distribution? Qualitative data. Questions about qualitative data? All right, quantitative data have different scales. Interval scale data are data that are ordered, the numbers actually mean something, and the numbers are the same unit apart from one another. So a classic example of this is temperature. If you go from 0 degrees centigrade to 1 degree centigrade, that means the same thing as going from 39 degrees centigrade to 40 degrees centigrade. Now, what an interval scale data doesn't make sense to do is if you're sitting at 25 degrees centigrade and somebody else is sitting at 50 degrees centigrade, this individual is not experiencing 2 times the heat of this individual. So multiplying and dividing and things like that don't make any sense with these types of data. On the other hand, if you're counting eggs from my chickens, if on day 1 my chickens produce 3 eggs, and on day 2 my chickens produce 6 eggs, on day 2 I got 2 times the number of eggs that I got on day 1. This is what it means to be ratio scale data. Operations like multiplication and division make sense with ratio scale data. Those things don't make the same amount of sense with interval scale data. A person 3 feet tall is half the height of somebody 6 feet tall. If it's 600 miles to Dallas and it's 300 miles to Oklahoma City, Dallas is twice as far away as Oklahoma City is. Those are ratio scale data. Quantitative data, regardless of whether they are interval or ratio scale data, they can all have averages calculated from them because they're ultimately numbers. But what you can't do is you can't take 25 degrees, multiply it times 2, and get 50 degrees out of it. So lots of data happen in this ratio scale data category, but not all data fall into that category. So it's important that you think about what the scale of your data are when you are looking at data. So for example, if I have 2 categories of people doing Facebook in class and people not doing Facebook in class, those are 2 categories. I can't do any complex mathematics on those things. So there's a hierarchical structure to data types. Nominal data is the most basic type of data, naming things, putting labels on things. Ordinal data, you have names, you have categories, and those categories can be ordered. Interval scale, there's an inherent order. 1 is greater than 2, 2 is greater than, 1 is less than 2, 2 is less than 3, 3 is less than 4. But multiplying and dividing those things doesn't make any sense. And then ratio scale data, there's an inherent ordering to them because they are numerical, but they all have the ability to be multiplied and divided. Ratio data can be converted into nominal data. So you could take my chickens and I could just arbitrarily say any day that has 3 or fewer eggs is a low production day. 4 or 5 eggs is a medium production day. And 6 eggs or more would be a high production day, especially because I only have 6 chickens. If I got more than 6 eggs, that means that one chicken produced 2 eggs in a 24-hour period, which would be unusual. One day since I've had chickens, I've gotten 7 eggs. So I can take this ratio scale data and convert it into ordinal data if I want. But what I lose is I lose some information in the process of doing that. One, I lose the ability to do complex math on it. I can't calculate means, because if I have 3 days where my chickens produce a low number of eggs, 2 days where they produced medium eggs, and 1 day where they produced a high number of eggs, how do I calculate the average number of eggs from that? You can't, can you? What happened the other day when we were going through basic R and I asked you to multiply the numerical assignment of the day, sorry, not the numerical assignment, the number of eggs to the written out version of the day. I asked you to take the eggs column and multiply it times the day, which was expressed as Sunday, Monday, etc. 3 eggs, 4 eggs. What happened when I asked you to multiply those to one another? We got an error message because you can't do that. You can't multiply a name times a number and get an answer. There is no answer to be had. In the same way, we can't take 3 days that were low, 2 days that were medium, 1 day that was high, and figure out what the average number of eggs per day is. Because we've taken these ratio scale data that you could calculate a mean on, and we've converted it to ordinal scale data. So we can go and take this data, convert it into interval data or ordinal data or nominal data. What we can't do is we can't take nominal or ordinal data and convert it into interval or ratio data. Now, you've probably heard people say you can do that, but R has already demonstrated to you that you can't do that because if you try and do that type of calculation in R, it's going to give you an error message. Questions? Whoa. What happened? Okay. There is a company called Conjointly on the web. They will actually offer to do statistics for you. They will design studies for you. They'll conduct surveys. They will analyze the data, and they will write you a report. My advice to you, do not give Conjointly your money. And here's the reason why. They have an article on their website called Types of Data. Just start reading. It's a couple of screens worth of data, worth of reading, but just read. Raise your hand when you've finished this first page. You went to the conjointly website? Nice. Raise your hand when you're done. Next section is bigger. The highlights and bolds are mine. They're not in the original version. Give me some indication of when you're done reading this. And the last little snippet. Why can I not spell agree today? What are your thoughts about this? Any of you ever taken a psychology class? Psychology studies oftentimes use Likert, what we call Likert scale data. This is a Likert scale. It's a 5-point Likert scale that basically asks people a particular opinion about something. In this case, Paul Rock's applied statistics. Do you strongly agree, disagree, neutral, et cetera, et cetera? What this author is advocating is that we can just put numbers on this. We could put numbers on this like 1, 2, 3, 4, and 5. And if 3 people answer here, those 3 people account for 3. These 2 people account for 4. These 4 people account for 12. This person accounts for 4, and this person accounts for 5. That's 19, 22, 23. That's 28. We can divide 28 by 11. And the average score would be 2.545. And this is how many social scientists treat ordinal data. These are ordinal data, and what this article is advocating is that you can just take those ordinal data, convert those ordinal data to some numerical scale, and then treat it just like if it was an interval scale or a ratio scale data. But if we didn't have these numbers, can you take these 3 statements, multiply them together, and get an answer? Can you take these 2 statements, multiply them together, and get an answer? You can't. Now, in this case, they're basically saying that these are interval scale data. Why am I saying that they're interval scale? They go 1, 2, 3, 4, 5. So they're ordered, so they're at least ordinal scale. But they're also interval because presumably the difference between 1 and 2 is the same as the difference between 2 and 3, the same as the difference between 3 and 4, 4 and 5, right? That's what it means to be interval scale data. And interval scale data, if these are really interval scale data, these data, you could do this too. You could just convert them to numbers and you could do this math. If you ask yourself not how I'm doing in applied statistics, I like caramel M&Ms. How many of you would strongly disagree? Nobody's strongly disagreeing. How many of you would just disagree? How many of you are neutral about caramel M&Ms? 1, 2, 3, 4, 5, 6. Did you raise your hand? 6 are neutral. Strongly agree. Or sorry, agree. 3. Wait, did you already vote? No, 3. 3 agree. And how many strongly agree? Yeah, baby. Strongly agree. To convert these things to ordinal, such that this was a 0, this was a 0, this was 18, this was 12, and this was 10. Now we have 12 individuals because I answered as well. That's 30, 40, 40 divided by 12, 36, 40, 3.33. This would be our average preference score, our average likability for caramel M&Ms. Ms. Frohnberger, how much do you like caramel M&Ms? They're your favorite M&M. Name me a candy that you would agree that you liked. Yeah, if I did another candy up here. So M&Ms, you strongly agree that you like caramel M&Ms. What would be your next most favorite candy?
I'd say sour Skittles.
What?
Sour Skittles.
Sour Skittles, okay. So on a scale of strongly disagree to strongly agree, M&Ms are here. This is neutral. Where would Skittles be on the scale? Right there. Okay. So that would be kind of the agree point, right? What's a candy you really despise? I couldn't pay you enough to eat it.
Snickers.
Oh, Snickers. Interesting. This would then be the disagree point. How far away is Snickers from that? Huh? Pretty far. Is it 1, 2, 3 units away? Is it further or closer? Snickers are out here somewhere. So your strongly disagree is 1, 2, 3, 4 units away. The problem with ordinal scale data, if you want to convert it to interval scale data, these divisions have to be reasonably assumed to be equal distance apart. For me, I can agree about a lot of things. I'm fairly agreeable. For me to strongly agree about something, it has to be something like caramel M&Ms. What's my next favorite candy? I like Nutrageous quite a lot because it's got everything. It's got sweetness. It's got some protein in it because it's got peanuts. It's got chocolate, which is, for me is a prerequisite for any candy. But I'm not nearly as jazzed about M&Ms as I am about Nutrageous. If I walk into a convenience store and I'm on a road trip, I'm just as likely to pick up a bag of jerky as I am to pick up a nut radius. I would agree that I like nut radius, but the distance between caramel M&Ms and nut radius is way more than the difference between nut radius and beef jerky. I'm much more likely to pick up a nut radius than beef jerky, but those two are much closer, and I'm kind of neutral about beef jerky, quite frankly. So these things have to be assumed to be correct intervals away from one another. If you can't assume that, if that's not a reasonable assumption, then you can't just apply numbers to these things and then do regular math on them. And I would argue that for most people, the distance between disagree and neutral, the distance between neutral and agree, is a much smaller difference than the distance between agree and strongly agree, and the distance between disagree and strongly disagree. And if that's the case, if these distances are more than these distances, or it could be that these distances are actually narrower than these distances, you can't just assign these numbers to them, because what you would have to do is you would have to make your scale something like 0 to 6 or something like that. In either case, is neutral 3/5 of strongly agree? Does that seem like a reasonable question to ask? No, it's kind of a weird question to ask, isn't it? It just what is 3/5 of strongly agree? Just to beat this point home further, what's coming up this coming week? What starts February 4th? What? February 4th, not the 14th. You're really eager for Valentine's Day. Anybody know what's coming up on the 4th? It's the beginning of something that's going to take weeks. Playing out in China. The Olympics. What's that? Oh, what'd you say?
Forgot about those. Forgot about those.
Oh yeah, I forgot about this. Yeah, because they're embroiled in international controversy at the moment. Because the United States is not sending any official delegates, diplomatic delegates, to the Olympics. What's your favorite Olympic event? Summer, winter, I don't care. Gymnastics. What specific event within gymnastics? Floor events. What? Anybody else have a favorite Olympic event? Swimming? Like distance sprints? Okay. Anybody else? I'm a huge fan of the 100-meter sprint. So, if you think about Olympic medals are categories. Gold is the fastest, silver is the next fastest, bronze is the next fastest. If these things were something other than ordinal data, you should be able to add, subtract, multiply, and divide them. So you have 3 people. They're all involved in swimming events. One person scored bronze in everything. One person scored 2 goals and didn't place at all in anything else. And another person scored 3 silvers. If you add these all up, they all sum to 6. 6 bronzes, 2 golds, 3 silvers. If you rank gold the most at 3, and if you rank silver the second most at 2, and if you rank bronze at 1, they're presumed interval values. Which of these athletes would you rather be? Person 2. How many vote for person 2? How many vote for person 1? How many vote for person 3? You'd rather be person 1? You'd rather have 6 bronzes than 2 golds?
Pretty impressive, I think. Yeah, you got like 6 medals.
You are consistent. You have 6 medals, but none of them are the gold medal. And the majority of your peers disagree with you. I think most athletes would prefer even a single gold to any silver or bronze without the benefit of a gold. Because they're not really equivalent. You can't just add up 6 bronzes and say, I've made 6 bronzes, I got 2 golds. It just doesn't make any kind of rational sense. Why does it not make rational sense? Well, let's just look at the 100 meter. These are the times for the 100 meter in the 92, 96, 2000, 2004, 2008, and 2012 Summer Olympics. They're all, for the most part, sub 10. There are a couple of these that are just slightly over 10 seconds. These people are blazingly fast. They're the fastest people on the planet. But look at the distance. Look at the time differential between gold and silver. In 1992, they were basically neck and neck. Neck and neck. Not neck and neck. Neck and neck. Really not neck and neck. And not quite neck and neck. You guys know what this year was? This is Usain Bolt. Have you seen the video of Usain Bolt winning the 100 in the Olympics? He was so far ahead of anybody else in the field. They were 2 or 3 strides away from him. That's how tight time is in a 100 meter. 0.2 of a second in a 100 meter is an eternity of time. He didn't win the gold. He crushed everybody else in the race. But you know what he got for that crushing win? He got a gold medal. Same as this guy who won by 100th of a second. The person who was so crushingly defeated and took silver after being humiliated by Usain Bolt, guess what he got? He got a silver. But he was way further away from Usain Bolt than this guy was from whoever won that year, whose name we quite frankly don't remember. You know why? Because the next Olympic, Usain Bolt wiped the memory of all other sprinters off the face of the earth. These are ordinal categories. They're not interval scale data, because if we look at the intervals, crushing win, devastating win, humiliating win that year. Have you ever seen the video of this? You notice what happens in this heat? Go watch the video. Homework for Wednesday. Watch the Usain Bolt Olympic win. Watch what he does at the end of the race. Well, just go watch it now. It's literally a 10-second flick. I believe so, yeah. Oh no, I'm not connected to the internet for some reason. Are you guys connected to the internet? Oh, I cannot seem to get connected. Scroll ahead until they do a lot of preliminary. Scroll ahead until the race. I'm watching it. Oh, there he goes. He pulls up at the end. He gets past everybody else. He's blowing everybody else, and then he stands up, full stature, which you should never do when sprinting. Stands up full stature, starts looking around to see where everybody else is. Imagine what he would have done if he had gone all out for the whole race. He pulled up and slowed down. You can do actually a quantitative analysis of his acceleration. You see him accelerating all through the entire 100 meters, and then at the end, he decelerates. He would have crushed it even more had he not done that. Each of those gold medals is not equivalent in a quantitative interval or ratio scale way because of this figure right here. This is a way more significant gold medal win than this was. Difference between gold and silver was a hundredth of a second. Difference between silver and bronze was a hundredth of a second. Just no way that you can really compare equally this with this in a quantitative way that is on an interval or ratio scale way. But in all these cases, one person walked away with the gold, one person walked away with silver, one person walked away with a bronze. There are appropriate ways to handle data, and there are inappropriate ways of handling data. Categorical data can be analyzed, but they can't be analyzed the same way that you would analyze quantitative data. So going back to this, I disagree with this website's take on things in a number of ways. First, I think this person is incorrect in thinking that people think that qualitative data are somehow inherently inferior to quantitative data. One of them is not superior to the other, they're just different. As a result of that, we have different statistical techniques for analyzing these data, and you should use techniques designed for qualitative data when you have qualitative data, and you should use techniques for analyzing quantitative data when you have quantitative data. And you shouldn't take qualitative data and try and convert them into quantitative data in the same way that you shouldn't take quantitative data and try and convert them into qualitative data. In the first case, when you take qualitative data and convert them into quantitative, it just doesn't make any sense because they're just verbal statements or categories. And in the same way, you shouldn't take quantitative data and convert it to qualitative data because you lose information. You lose the ability to do things like calculate means and standard deviations and confidence intervals on them. So treating data appropriately is useful. In the same way, all quantitative data is based on qualitative judgments. Not really true, and all qualitative data can be described and manipulated numerically. Once again, not really true. So my advice is don't allow conjointly access to your data. So, quiz time. The first one up there, is that quantitative or qualitative? Qualitative, is it ordinal or nominal? Second one, pounds of corn in a bushel of corn. It's quantitative. What level of quantitative is it? Interval or ratio? It's ratio because if you have 20 pounds of corn, it's half as much as 40 pounds of corn. Colors. Nominal, qualitative data. Yep, because one color isn't any better than the other. What percentage of your day do you feel anxiety? Well, it's asking you to estimate a percentage. I think it's quantitative. Now, I've paired a quantitative measure with a touchy-feely kind of question, which makes you want to think that it's qualitative. But if you say, well, what percentage of your day as an undergraduate student do you feel anxious? If you say 50%, that means that 50% of the time, half of your day, you spend feeling anxious. How many of you are in the 50% category? Good. How many of you are more than 50%? That's not so good. How many of you are less than 50%? Okay. 10%. 20%. 30%, 40%, 2.5%. You can put a number on it. So if you really only feel anxious 2.5% of your day, if your day is 16 hours long and you spend 8 hours sleeping, you could actually calculate the number of hours that you feel anxious. So is this quantitative or qualitative? I would argue it's quantitative. Is it interval or ratio? Why would it be ratio? Yeah, you could say if Elizabeth feels anxious 50% of the day and Claire feels anxious 25% of the day, Elizabeth is twice as anxious as Claire is. So that would be ratio scale. Number of eggs we already talked about. What is it? Quantitative, qualitative? Quantitative, interval, ratio. Did you say interval? Is it interval or ratio? It's ratio because 10 eggs is twice as much as 5 eggs. Number of seconds required to run 100 meters. Quantitative, ratio, or interval? Ratio, because if you're running it at 10 seconds and somebody else is running it at 5 seconds, they're running twice as fast. Body temperature in lizards. Quantitative, interval, or ratio? Interval, because a lizard that is at 35 degrees centigrade is not twice as hot as a lizard that is at 16.5 degrees. No, 18.5 degrees. So, knowing what types of data fall into which categories determines to a certain degree what kind of analysis you can do on those things. All right. Wednesday, I will be showing you how to calculate confidence intervals. So we won't be doing anything in R, but we will be doing some calculations. So I would advise you to bring something that you can write on, because here at the beginning, and this is, I think I told you this the first day, everything that we do in this class, we will always do first by hand, because doing things by hand teaches you how something operates before we ever start doing it on computer. So the R script that is on the Moodle site from last Friday is the R script that generated those distributions today. You could go back and recreate that for yourself and see how all of that works if you want. That's the purpose that R script is there for. All right. Any questions? All right, I'll see you on Wednesday.